So we move to the next talk, last one before the coffee break, if you're worried, by Professor Jonathan Ruhman on measurement-induced phase transition.
So thanks. I'm actually filling in for my department head, Efrat Shimshoni, who couldn't make it today. So I hope I'll do a proper job. So as mentioned, what I'm going to talk about is this field that we're interested in physics. It's called measurement-induced phase transitions. Anyways, this is a new phase transition that we've discovered in the dynamics of quantum systems that are evolving unitarily, but also undergoing measurement. This is what we call monitored quantum systems. And the early work was done with my collaborators, Adam Nachum and Brian Skinner, but I also want to acknowledge the more recent work was done by my talented PhD student, Einat Buz-Nachachituf. So I want to start by somehow I'm going to use some diagrammatic representations. So I need to make sure that everyone's on the same page. So I'm going to show these kind of diagrams a lot. And while I know that what you should have in mind when you look at this picture is that this is a drawing of a rug, obviously, but for me, this is actually going to be a unitary operation. So it means that this gray rectangle is a matrix acting on these, for example, qubits at the bottom. I apologize, I'm a physicist, so sometimes I switch between 1 and 0 and up and down for spins. And these can be, for example, some unentangled qubits that are initiated in the 0 state. And then time is flowing upwards, so I also apologize to the quantum information scientists. I don't draw quantum circuits from left to right, but from up to down, because that's obviously the right way to do it. I don't understand why you would ever do anything else. Anyways, this rug, I will also allow myself to break it into small elements, like you would do with, for example, universal quantum computation. You want to break your huge unitary operation into small, say, two-side gates, for example, and that's what these small rugs mean. Okay, good. So let me first motivate the existence, or give you some intuition for why such a phase transition should exist in the dynamics of quantum systems. And to do that, I just want to remind you that if you have a closed quantum system that is evolving under some generic unitary dynamics, then generally the system goes, especially if you start from a product state, as time goes by, entanglement tends to grow and grow and grow. You need to do something very special to generate a huge superposition state and not have it strongly entangled. So that means that generic unitary evolution, whether it's on your favorite physical system, or whether it is some generic quantum computation that you want to do, and there's the question of what that quantum computation would be, as was raised in the beginning. But if it's generic enough, then it would cause entanglement to grow. On the other hand, if afterwards, if I measure some of these qubits, then that immediately disentangles them, assuming some ideal measurement. It will project these states to some well-defined state, and then it will break them out of this superposition and suppress entanglement. So this already shows you that there's a competition between one effect that tends to enhance entanglement in the system and the other one that suppresses it. And our prediction is basically that if you have this kind of monitored quantum systems, these are systems that undergo both unitary evolution and measurement kind of in parallel, then there can actually be a phase transition. So you can imagine that there is a notion of a density of these measurements, which is basically how dense they are in space and how frequent they are in time. It's kind of like a 2D density in this case, 1 plus 1D space. And as a function of this density, if we just distribute them randomly, it turns out that there is a sharp phase transition in the thermodynamic limit between one phase where the measurements are not frequent enough, and then the system is capable of developing an extensive amount of entanglement, or if you like, it kind of ergodically probes its Hilbert space, or at least some regions of it, and a second phase where the measurements are too frequent and the state collapses and basically focuses to some corner in the Hilbert space. This is, of course, just to give you some intuition, but we're talking about a many-body system, so this should be some generalized Hilbert space or Bloch sphere. Okay, so so this is basically the prediction that there is such a phase transition. Now, the first thing I need to mention is why should you care? Why is this interesting? So one perspective that I like in particular is that this phase transition actually implies a phase transition in our capability to simulate a quantum system. Now, why is that? Because when we want to simulate a quantum mechanical system that is open to the environment, we basically have roughly two approaches that we can take. One of them is to just simulate the dynamics of the density matrix using some sort of Lindblad evolution. But then there is another approach, which is much cheaper numerically, which is to evolve a wave function. Of course, there is a price we need to pay, because once we go to a wave function, we have to add a stochasticity to the equation, and this is called the quantum trajectory picture. So we basically evolve the wave function, and because it's open, it can sometimes jump. And these jumps are very much like the measurements I just showed you before. They can occur during the dynamics, and each one of these trajectories has its own probability, and then we can reconstruct the density matrix by summing up all of these trajectories together as presented here. And you can reproduce the same density matrix in this. So what this actually means is that if the coupling to the environment is strong enough, then each one of these trajectories is very easy to simulate on a classical computer, because it has a small amount of entanglement, and then we can store it, for example, in something like a matrix product state easily. On the other hand, if the coupling to the environment is too weak, we can no longer simulate it on a classical computer, and I would say that that's already some sort of threshold for quantum advantage, right? Because as long as I cannot simulate it on a classical computer, at least as an idea, then there must be some potential advantage in this dynamics. Because this is Cyber Week, I should also mention the cryptographic perspective on this, although I don't understand it very well, but some people have been discussing the relationship between this phase transition and the ability of an eavesdropper to decipher a code, for example, so with relation to the previous talk. So the idea would be that imagine that you have an eavesdropper like this who's trying to extract the state of the system. Well, one approach to avoid that could be to try and scramble the quantum information using unitary gates, and that makes it very difficult for the eavesdropper to extract the information of the state. And it turns out that if we're in one phase, this phase where the measurement or the ability of this eavesdropper to measure the state is below the threshold, it will take him an exponentially long time in the number of qubits to extract the state of the system, while in the other phase, it will take him something which is polynomial in the number of qubits. So that's also important from that perspective. Okay, so now I've motivated maybe why you would want to be interested in this. I also want to mention that it's extremely challenging to observe this phase transition in an experiment. And the reason is because it's actually only observed within a single trajectory. So that means that if we, at least if we want to do it straightforwardly, then we have to kind of post-select the whole sequence of measurements to be the same every time. If we want to do any kind of measurement at the end, for example, do some kind of quantum expectation value by taking many, many shots at the final state, we would have to make sure that the sequence of measurements along the way is exactly the same. Otherwise, the information about this phase transition will be washed out. So that's, I think, maybe the overarching challenge for people like me is to understand whether this phase transition even has a physical consequence or whether it's just a theoretical concept. So that's an interesting thing. Nonetheless, there have been attempts like Google, IBM, and IonQ have all performed experiments to show that such a transition exists. It's only a proof of principle. It's small system sizes and a huge amount of shots. It's basically a brute force approach with a lot of clever techniques to reduce error and so on and so forth. Like it's extremely, it's a heroic effort, I would say, but it's kind of still trying to just show the transition in the most straightforward way. Okay, so now that I've motivated and explained to you about this measurement phase transition, let me tell you what I'm going to talk about in this talk. So what I want to do is I want to give you an intuitive picture to understand at least how we predicted this phase transition, how you can understand it. Then I will tell you about numerical simulations that we've performed. And then if time will permit, I will talk about more recent works. Okay, so let me start from an intuitive picture. So when I talk about entanglement, up to now I talked about entanglement kind of freely and not in a concrete way. We need to be able to quantify it. What do I mean by a lot of entanglement or a small amount of entanglement? So the simplest possible way you can think about it is known as the entanglement entropy. And this is based on the concept of what is known as a Schmidt decomposition. Imagine, when you talk about entanglement, you're always talking about entanglement between something and something else. So imagine I want to know how much subsystem A is entangled with subsystem B. Then I can Schmidt decompose the system into sum over product states with these probabilities. And these probabilities basically tell me how much entanglement is between A and B. And we can, for example, take these probabilities and create a Shannon information entropy out of them. And then that will tell us how much we will be surprised every time we measure, if we would have a measurement device that can measure this very specific states. And so this is this von Neumann entropy, and it's bounded from above and from below by this generalized, what we call Renyi entropy. This is just a tool that we can use sometimes if we want to compute this. Okay. So, in order to understand the origin of this phase transition, we developed this idea that if you want to estimate the amount of entanglement in a state, if you want to do it exactly, you need to use something known as a singular value decomposition. That's very expensive numerically. But there is a cheaper way, which is only based on the geometry of your circuit. You don't need to do any computation. Just ask what is the structure of your circuit. And this is known as the minimal cut principle. The idea is that, say, this is subsystem A and this is subsystem B, and this is the circuit, this set of rugs is the circuit that generated this state. So the claim is that if you propose some sort of cut through that circuit that cuts the two halves, then the number of bonds that you cut is always an upper bound on the entanglement entropy. And the idea you can think about it is you can contract all the internal indices in these connected rugs, and then you find that mathematically what this picture actually means is just writing your wave function in something that looks like a Schmidt decomposition. But of course it's not a Schmidt decomposition because it's just some random cut that I proposed. But the idea is that if you minimize over all these cuts, then you get exactly what is known as the Schmidt rank, and this is an upper bound on the actual entanglement in the system. So this is what we will call S naught. It's an upper bound on the entanglement. And using this technique, for example, we were able to show that if you evolve your state randomly, using gates that are distributed kind of randomly, then you get entanglement growth, which can be mapped to statistical mechanical models of surface growth, the KPZ equation, which tells you, for example, how snow accumulates on a window, or how a fire propagates, a fire front propagates, and so on and so forth. So this is very nice. We can make a connection between simple heuristic pictures in statistical mechanics and entanglement growth. Okay, so how does this connect to our phase transition? So to do that, I need to add another element to the story, which is the measurement. So what do the measurements do to this minimal cut picture? The idea that I want to argue is that once we measure a qubit, if it's an ideal measurement, then we project it back to its initial product state. And by that, we kind of, as far as the minimal cut is concerned, it's kind of like decimating a bond. And those of you who are familiar with the phenomena of percolation can already identify that there is a phase transition here. There's a percolation phase transition. But because this is a cyber week, I suspect that not everyone in the audience knows what I mean when I say percolation. So let me take a small detour and explain what I mean by percolation. These signs were something that I was extremely frustrated in the morning when I would take my son to school when I did my postdoc. But I hope you won't be frustrated by this small detour. So the way I like to think about percolation is the following. So imagine that you have some kind of topographic map. Okay, so these lines represent height lines. And there's a storm outside, so maybe the water is accumulating, it's raining and raining and raining, and then you start to develop puddles at the minima of this potential. And as it rains more and more, these puddles will grow into lakes, right? And grow on until there is something that is known as the percolation threshold. There is a critical point where all these bodies of water kind of connect. And actually, if you look at it, you can see that you can't really distinguish between the structure of water and land. They're kind of dual to each other. And indeed, if it rains even more, then eventually the land will separate into islands, and these previously lakes will become just one big sea. Okay. Now, how is this related to our story? Why is that important? These two phases would feel very different. For example, if you're this guy over here, you're carrying a boat, and you want to get, say, from this side to this side, like this minimal cut I was describing before. In this phase, what's going to happen is that you're going to have to carry this boat on your head from lake to lake. And as much as you might enjoy the occasional lake to sail on, eventually you'll find yourself walking a distance that grows linearly with the depth of the land you need to traverse. On the other hand, if you're in this phase of the system, then you're kind of like Moana, right? You just need to walk to the nearest shore, and you can sail anywhere you want to. Okay? So what this implies, okay, so this is the end of our detour. We can go to the kindergarten, and what this implies, it implies that if we're looking at this minimal cut picture, it will undergo such a phase transition. There's going to be, okay, I'll go back to this in a moment, but what I want to argue is that basically there's going to be one phase where the upper bound on entanglement is going to grow linearly with time. This is this annoying phase where you need to go between lakes, and then the second phase is where you just need to go to the nearest shore, and then you're home free. And the entanglement entropy is basically bounded by a constant. And I also want to acknowledge Dorit Aharonov, who in the 2000s already identified this connection between quantum circuits and percolation. Okay, so just to show you that this idea works, by the way, how much time do I have? 10 minutes, okay. So just to show you that this idea works, we simulated quantum circuits using this package iTensor and looked at this upper bound on the entanglement entropy. It's basically the number of eigenvalues in the reduced density matrix as a function of time for different values of the measurement density. And what you can see is that it generally kind of rises linearly and then plateaus. Okay, and then we can take this value of the plateau and plot it against P. Okay, this is the infinite time entropy as a function of P for different system sizes. And you can clearly see that there are two phases. There's one phase where the value of this plateau doesn't depend on system size, meaning that the amount of entanglement in the system is not bounded by, it's bounded by the measurements and not the system size. And a second phase where it's growing with system size. And then we can also use a finite size scaling with no free parameters because we know everything there is to know about percolation theory, and you can see perfect data collapse. So this tells us that this idea works, okay? Now let me go to the, all this was just an upper bound on the entanglement entropy, but the question is, what about the real entanglement entropy, which is what interests us? And then what we did is we basically look at the von Neumann entropy. And you can see that the von Neumann entropy has a similar behavior. Basically, there is one phase where the entanglement, the saturation value of the entanglement entropy doesn't depend on system size, and a second one where it does. And this is the transition between this volume law phase and this area law phase that I was describing in the beginning of the talk. But a very interesting fact, at least for me as a physicist, is the fact that this transition doesn't occur at the percolation threshold. It's actually shifted to a lower value. Okay, so this is something we know in physics. There are many examples for some sort of mean field or classical transition. Once we make it quantum, then we can get a shift in the location, and that opens a path for a lot of interesting physics, such as questions like what is the nature of this transition. I want to point out that there's still controversy on where this transition actually occurs, because if you look at different measures, this is something more similar to what is known as a Binder cumulant, where you have a crossing of some quantity. This is the tripartite mutual information in a system with periodic boundary conditions, and the crossing occurs at a different value, and the critical exponents don't work. So we're really lost on what is the theory, what is the properties of this phase transition. Okay, so yeah, so this is basically the bottom line, and if this is all you get from this talk, that's enough for me. So from the physics perspective, there is this new type of phase transition that we don't understand, and we would be really interested in finding a way to understand it. And what these three regions actually mean is that you have one region where your quantum circuit is connected and can also transfer quantum information or entanglement through space and time. A second phase where the circuit is still connected, but there are too many measurements such that kind of information decays over a finite length scale or time scale in the circuit. And then finally, a phase where it's physically disconnected by these measurements. Okay, so now let me tell you a little bit about the work we're doing right now. I don't have much time, and also I don't think it is that crucial. You're not biting your nails for our latest results. But I just want to mention that there are two things that we've been doing recently. One of them is Clifford circuits. I've been looking to kill Clifford circuits as a tool to study this problem for a long while. And the reason is because Clifford circuits allow classical simulation, as you know, through the Gottesman-Neal theorem. And that means that you can simulate huge system sizes. And people were studying this and claiming that it might have some non-trivial features in it related to quantum mechanics. And as we know, Cliffords are very suspicious because they act really classically. So we wanted to show that this is just a classical percolation theory. And the second one is more in the other direction. We actually wanted to get some analytical control over the transition, and that we did by changing the structure of the circuit. Instead of like a 1D circuit that looks like a rug, we made it into an all-to-all circuit. So let me just quickly tell you. So this is the phase transition that was observed. These are actually, when we published our paper, it was in competition with a group of Matthew Fisher, Yaodang Li, and Xiao Chen. And they actually proved that this phase transition exists using Clifford circuits. You can see the huge system sizes. And as you can see, the transition occurs at a value of P. The structure is the same, but it doesn't happen where the percolation threshold happens. It happens at a much lower value. So to study this, we took some specific model. So these are the Clifford gates we take, and we have two parameters, P and R, and then we have a phase diagram. And in this phase diagram, there is a boundary, which we computed, between this volume law or entangling phase and area law, where measurements are too strong. And the reason we took this model is because it doesn't have a percolation transition anywhere in the phase diagram. And my talented student, Einat Buznach, figured out how to apply this technique known as ZX calculus to simplify these circuits, like rewrite these circuits using ZX diagrams and simplify them. And what happens when you do that is you get new structures, new kind of tensor networks, I should call them. And you can ask about these tensor networks whether they obey this kind of percolation transition. And Einat very nicely, her data follows the exact measurement-induced phase transition, which tells you that these Clifford circuits are just a classical percolation transition in disguise. And now let me just say a few quick words about all-to-all circuits. By the way, am I out of time? I have 2 minutes. Okay, 2 minutes. Oh, that's nice. Okay. So all-to-all circuits, we're changing the structure of the circuit now. We basically choose two qubits randomly and apply a gate between them, or measure one of these qubits randomly. That's the dynamics that we considered. And the idea here is that if you follow one of these lines, these what we call timelines of the qubits, you can kind of see that they branch out like a tree, both up and down in time. So we lose the notion of time, but we can think about each unitary gate like a branching point. So you can think about it like a tree structure. And here you can see an example of the circuit where you map a specific all-to-all circuit to a tree. And this is extremely useful because, of course, it's not really a tree because eventually it can connect to itself and create loops which don't exist in trees. But if you take the system size to infinity, the probability of that happening goes to 0. So then we can study trees. Now, I'm not going to talk too much about how we study trees, but the idea is that we look at the amount of entanglement between the stem and the leaves of the tree. And it turns out that if you look at the probability distribution function of the eigenvalues of this entanglement or the density matrix for that bipartition, then you can try kind of study the distribution. Statistically, you can study the distribution function of these eigenvalues, and you find that there are two phases, one where it kind of grows and the other one where it shrinks. And the velocity of the wavefront follows a phenomena that is also known in capillary gravitational waves, where you kind of have a minimal velocity. And finding this minimal velocity allowed us to identify the location of the transition exactly, which we were very excited about because now we have an exact value for the phase transition, and we can also identify the critical behavior close to that transition, how basically the entanglement grows near the transition. So we proved two things here. The phase transition exists. It's a completely different universality class, and it's distinct from the classical percolation threshold. Okay, so with that, I think I'll finish. I'll just reiterate that there are these entanglement transitions that occur in monitored quantum systems. We have a theoretical challenge because we don't have a theory for this transition, and that's a very interesting, I think, problem. There's an experimental challenge to observe it, and then I think that there's a concrete connection to many fields in quantum mechanics, and it's, I think, also an interesting direction is to try and connect it to all these different topics, which is something that is being done. So thank you.
Okay, thank you, Jonathan, for this very nice talk. We have time for 1 or 2 questions.
Yes, there is. I think the nicest and the most general one is called purification.
Yeah.
So you can imagine, or maybe I'll repeat the question. Are there any other diagnostics for this measure, for this transition except entanglement entropy? And I think the most beautiful one, in my opinion, is the concept of purification. You can imagine that you start from a fully mixed state, actually. And this can be related to, this key distribution. For example, imagine that there's, Alice and Bob, and they share a lot of entangled information between them. And then there is this eavesdropper that is trying to attack the state. But, for example, Bob, I don't know, and then Bob is trying to avoid that by scrambling. So you can ask what is the, how mixed the reduced density matrix of Bob is. And that tells you how much it shares information with Eve. This is a concept of purification. And we can also tie it to something that we like to call operator entanglement entropy, which is basically how much information does your non-unitary evolution transmit through time. And that's actually, I think, the most fundamental observable. But then I think that what I was mentioning before is that physically, like if I want to do an experiment, I don't know how to measure such things. So that's a challenge.
My second question is about the phase transition point. Is it necessarily a conformal field theory?
So people think that it's a conformal field theory. It shows conformal invariance, all sorts of properties related to that. So yeah, that's what the community believes. But again, there is no a theory. So people try to write theories. You can write theories that have the right symmetries. There are paths to do that based on replica theory, but no success yet.
Thank you.
Okay, thank you very much. So I think we should finish now.